rotation matrix and trigonometric addition formulas. There are so many ways to derive addition formulas. You know how to compute cosine alpha plus beta and sine alpha plus beta. But matrix representation introduced by Descartes' way, originated from the computation of a scalar product, is a remarkable invention. This is represented by matrix product. In mathematics class, they don't teach you in this way because they don't know the origin. The origin of matrix is physics. Don't forget. Okay, so using this method, we can find the addition formula very easy way. We recall this diagram. This one represents the two basis vectors of original coordinate system, and I have introduced a new coordinate system whose basis vectors are primed. We know very well about the directional cosine, that is the scalar product of any two original vector and the rotated vector. And using this way, we know these two triangles are congruent, and this side is cosine and this is sine, cosine and sine. It is in the first quadrant and this is on the second quadrant. I can compute these scalar products as cosines because cosine here, this is a half of pi minus theta, and this one is a cosine half of pi plus theta. Everything can be expressed in terms of sine and minus sine. As a result, we have obtained the rotation matrix in 2 dimensions. It is interesting that the rotation matrix in 2 dimensions is commutative. It is commutative because you rotate by just like what you see every day. The dials of a clock rotates. So angle of rotation theta 1 and theta 2 can be exchanged. For example, say after first rotate by theta 1 and theta 2, and we can exchange the order of rotation, and you can rotate by theta 2 first and theta 1. In any case, the final result is the net total result is a theta 1 plus a theta 2. This is true only for the 2-dimensional case, and in general, in 3-dimension, rotation is in general not commutative, but in 2-dimension, it is trivial, it is commutative. Okay, so if you wrote, but this is a clockwise rotation, but if we analyze physics problem and mathematics problem, it is convenient to fix the rotation anti-clockwise, opposite to clock's direction. So theta 1 rotation first and theta 2, and theta 2 first and theta 1, they are equal. Therefore, if you rotate a vector whose original components are A1 and A2, after the rotation about the z-axis by an angle of theta, you need to multiply these original components by this rotation matrix, cosine, and this is plus sine, minus sine, cosine. So if you multiply this, your new components, that means a new vector after rotation keeps the basis the same. It is different from mathematics. Components varies, and these new components are obtained by multiplying this rotation matrix. If you rotate this one order, then it is this. Original components are on the right side, so first rotation is this, and second rotation is this. But as you know, it is equivalent to a single rotation by theta 1 plus theta 2. So product of these two rotation matrix must be equivalent to a single rotation matrix with a single angular parameter. And as shown in this figure, rotate by theta 2 first, and then rotate by theta 1 next. They must be the same. From this, we can prove this addition formula for the trigonometric functions. Okay, let's see. It's simple. First of all, as you know, this is a single rotation. So why don't we rotate by alpha and beta? So beta and alpha. And actually that is the same as alpha first and beta next. So we know this. And this angle substituted to the original formula for the rotation matrix. Then I would get cosine, sine, sine, cosine, negative sign. You have to remember this is a positive, this is negative for positive, the active transformation. In passive transformation, in mathematics textbook, it is opposite. You have to remember it very carefully. Okay, anyway, using this one is the same as this, and why don't we compute the matrix product explicitly? I copy the same form, but arguments are alpha and beta. Why don't we compute the product? The former one, front one, should be computed with row, and this one should be computed column. First row, first column. Cosine, cosine. Okay? Sine, sine. But we have negative sign on it. All right. So this one, this, and this. Okay? Cosine, sine. Cosine, sine, negative. Sine, cosine, also negative. Okay? And this, and this. Sine, cosine, sine, cosine. Okay? Cosine, sine, cosine, sine. Okay. Last one. Two element. This one and this one. Sine, sine, minus. Sine, sine, minus. And cosine, cosine, plus. Everything is right. We have shown that this matrix product is the same as a single rotation about the sum of the two angles. Therefore, every element, 1, 1, we call this 1, 1, 1, 2, 2, 1, 2, 2 element. 1, 1 element is cosine alpha plus beta, and this is the same. And we notice that both of them, this one and this one, they are the same, and the value is cosine, cosine minus sine, sine. So the result is this. In addition, we can compare this and this. The sine alpha plus beta is a sine, cosine, cosine, sine. And the other one, they are the same, except that we have a total negative sign. Therefore, we have proved this addition formulas for the trigonometric function by making use of the commutative relation of the product of the rotation matrix. However, that is true only for the two-dimensional case, and in three dimensions, rotations is not commutative anymore. It is not always true. So once you have a counterexample that does not commute, then you will say the rotation is not commutative in general. So commutativity is only true in the two-dimensional case. Okay, let's see. We can see the shape of this matrix is identical to the two-dimensional rotation. Actually, rotation happens only in two dimensions because rotation, we have two components, x and y components, and after being rotated, this component contribute two components, okay? Parallel component and transverse component. So that's the reason why rotation is in general only on the two-dimensional plane, keeping any other dimension the same. Therefore, this structure is this. So I have introduced an axis of rotation in here. It is the rotation about the x-axis. Because the rotation is about the x-axis, there is no change in the first coordinate. The only change happens in the second and third components. And the rule is identical to the previous one. Why don't we consider the rotation about the y-axis? We have the, again, identical elements for the y component. There is no contribution relative to y. It's a y transformed into a y prime component only. After that, we should be very careful. If we had this one as a 1, 1 component, then I should have elements in such manner. However, they are lost. I have to copy this result. There is a place here, this empty place. I move this one to here. And then this one, where should I put it? This one should be moved in here. And this one is moved there. Therefore, I can construct the rotation matrix about the y-axis. The direct multiplication of the rotation about y-axis first and then x-axis next. You can compute this is rows and columns. After multiplication, you will find this complicated matrix. Why don't you exchange the order of multiplication? You rotate a vector about the x-axis first and then about the y-axis next. In that case, the matrix is exchanged, and after multiplication, you will get the result. Many of case in diagonal elements, you see diagonal elements are identical to each other. However, you will find these off diagonal, this diagonal, and these are not diagonals, it's off diagonal. Off diagonal elements are not identical to each other. So matrix product in general, we are working on the rotation matrix. Two rotation matrix, if the axes are different, these axes are different, rotation about different axes should not be exchanged. So commutative law does not work. It does not hold at all.